Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on computer aided drug design. We will continue on the topic of molecular mechanics, force field. So what did we talk about in the past few classes? There are different functional forms for force field. We have terms for stretching of the bond, bending, torsion, non-bonded. So they could be in quadratic form, okay, that is like Hooke's law, r minus r naught whole square, that is r is the new distance, r naught is at equilibrium, or they could be quartic type, that is raised to the power 4. As you can see, cubic is not generally preferred, or Morse type, e power, because when the bond lengths are very long, quadratic form gives very high energy. As you know, quadratic is square term, so the energy goes up in a quadratic fashion. So this approach is also followed. Boundary conditions: should I have the molecule in vacuum? That means there is no interaction with solvents or any other molecule of that type. It is more like a gas phase. So if I want to simulate gas phase, this is the best. Then comes solvent box. I put in a lot of solvents around it, so I explicit solvents. That means I put the molecules of solvent or implicit solvent. I can change the dielectric constant. Then comes periodic box. We have box where your molecule is inside, which is surrounded by a lot of water. So you have this type of box on all the 6 faces of the original box. It could be a cubic, or it could be a rectangular box. Okay. So if one water molecule goes out from one side, you assume another water molecule entering from the opposite side, so that the density is maintained constant, and generally periodic box is one approach which is very liked in most of the simulation studies. Then we talked about minimum energy conformation. That means as you know, molecule reaches a thermodynamic equilibrium where the energy is minimum. Okay. So you may have different conformations, but the energies may be higher, but you need to find the conformation at which the energy is minimum, that means most negative. So if you look at conformation on the x axis and energy of the molecule, so minimum energy conformation is this. Of course you may have local conformations also, like I said, if you start with some conformation and keep changing the conformation, calculate energies, you may come here and you may think this is the minimum energy, but that's not very true. Okay, that's not very true, or that's a local. Similarly, you may start from somewhere here, and as you go down and you think that's the minimum energy conformation, but that is also not true. But actually you need to reach this is the global minimum energy conformation of the molecule. So there are many approaches to arrive at this, starting from different starting conformation, and try to avoid the pitfall of local minimum. We will talk about that later. So these are the different things which we talked about in the past few classes, and we also looked at a demo of molecular modeling software called Marvin Sketch. Okay, this is a freeware, it is very good, and it is free for academic, for faculty. Okay, so you do not need commercial software for this. We can sketch molecule, that means we can draw molecules in 2-dimensional, and then we convert it into 3-dimension, and then we can calculate the energy, minimum energy conformation. Then we can calculate a lot of structural features, structural parameters, 3-dimensional structural parameters, a lot of so this is a very good software. We demonstrated last week, so I suggest that you go and then get that software. I think you have to register and so on, and then start playing with that. We can even take structures from say zinc, because zinc already has built in structures, many molecules, so we can take it from there and then bring it to Marvin view, sketch, and then look at the 3D conformations and so on. Or if it is a new molecule, we can draw it in the 2D pad available in this particular software. This is a very good software, so you do not have to think about going for a commercial software and so on. Actually, do not get fooled by commercial softwares. These softwares are good enough, and of course the number of force fields may be less. Okay, some commercial softwares may have many force fields and so on, but for academic purposes, for teaching purposes, training purposes, I think this is a very good software. You do not have to buy a commercial software. Okay, there are many reference books I am introducing here. I suggest you get some of them for your library and start reading them. Guidebook on molecular modeling and drug design, Chemi-Informatics, Handbook of Computational Chemistry, Computational Methods for Prediction of Drug Likeness, Molecular Modeling. So you can see a lot of books actually. This is quite a good book. So many different books are there. Of course, in this book you may find 1 or 2 chapters on molecular modeling. So you can read them. Of course, not all the books will cover all the topics. So some books may cover certain topics based on their focus. Okay, let us go further on this topic. What is this energy minimization? Okay, let us look at this energy minimization. Now you have to recall your calculus, which you must have studied long time back in your first year UG engineering. If you look at Taylor series expansion, Ux, if you want to expand this function Ux at the point xk, how do we write? Uxk plus x minus xk du by dx, and then substitute for xk plus x minus x square by 2 factorial d square u by dx square, or you can put dxk dxj, expand it at k and so on actually. Okay, this is called the gradient and this is called the Hessian. Okay, so there are algorithms which make use of only the gradient. There are algorithms which make use of this as well as this, and of course they do not calculate this analytically, but they calculate numerically. How do they calculate numerically? You take the value of, find out the value of u at one particular point, and then you find out the value of u at a very small incremental point delta. Okay, so the difference in the u values divided by delta x gives you du by dx. Okay, as you know, you must have studied du by dx can be approximated to delta u by delta x. Okay, delta u by delta x. Okay, because as delta x tends to 0, this will be equal to du by, sorry, this is equal to du by dx. Okay, so if you want to look at so the algorithms are classified by order or the highest derivative used in the Taylor series. Okay, first order methods common, you have steepest descent method, conjugate gradient method, and of course you have non-derivative methods, simplex method, sequential methods and so on actually. Okay, so if I am looking at a minimum, okay, then it should satisfy df by dx, or if you are talking about u, then du by dx should be equal to 0, and d square f by dx square should be greater than 0, because as you know, if you have like this, okay, x and f for example, if it is a minimum, okay, df by dx is equal to 0, okay, because as you can see the slope will be 0, and also when you take the second derivative it should be greater than 0 because it is increasing there. Okay, so for minimum, what are the two conditions? Df by dx is equal to 0 because it will be sort of a parallel line, that is the minimum, and then d square f by dx square should be greater than 0. Of course, for maximum, df by dx is equal to 0, d square f by dx square will be less than 0. Okay, so this is for minimum. So the criteria for a function f to have a minimum value with as you keep changing x will be df by dx is equal to 0, d square f by dx square is greater than 0. So, if you have simple small functions, you can do it analytically. We just differentiate with respect to the independent variable, equate it to 0 and then calculate the parameters, and then you cross check by say taking the second derivative and see whether the second derivative is greater than 0. Okay, that is for the minimum. Okay, so let us look at some simple thing. Look at this function y is equal to x square minus 2x plus 2. So, I want to find out the minimum. So, I take a so y is the dependent variable, x is the independent variable. It is a very simple problem, one independent variable problem. So, dy by dx is equal to 2x minus 2, okay, and then if I equate it to 0, okay. So, when I equate it to 0, it comes out to be x is equal to 1. Now, I need to find out whether this is a minimum or maximum. So, what is the condition for minimum? Here I had mentioned, right, d square f by dx square should be greater than 0. So, d square y by dx square, I differentiate again, it comes to 2, because this will become gone, this is 0. So, 2 and this is greater than 0. So, it is a minimum. So, if you plot it also, you can cross check, you can go to Excel and plot it, y is equal to x square minus 2x plus 2, this is y. So, I take different values of x, what happens? It comes down, down, down and then it goes up, because it is a parabolic relation at x is equal to 1 here, x is equal to 1. So, you see 1 minus 2, okay, x is equal to 1, okay. And at x equal to 1, dy by dx is equal to 2 minus 2, that is equal to 0. Okay. So, simple equation, we can even plot it in Excel and find that x is equal to 1 is the minimum value for x. Okay. Or how do you do it? We take a dy by dx and then equate it to 0, and from there you calculate x. To cross check whether it is minima, you take a second derivative d square y by dx square, here in this case it is 2, it is greater than 0. So, it is a minima. So, two conditions like I mentioned, we need to look at these two conditions for minima. Okay. Let us look at this is a one independent variable problem. Let us look at two independent variable problems, x and y, and z is your dependent variable. Okay. So, here how do I find x and y? I need to partially differentiate the z function and with respect to x and with respect to y, and then equate it to 0. So, if you take dz by dx, okay, partial differential, actually I should not put a dz by dx, I should actually put it like dz by dx, and here it should be dz by dy. Okay. So, if you put dz by dx, I am differentiating only with respect to x. So, 4x plus 2y minus 6 is equal to 0. So, similarly dz by dy, and this will not come, 2x plus 4y is equal to 0. So, I have 2x plus 4y is equal to 0, 4x plus 2y is equal to 6. Okay. 4x plus 2y is equal to 6. Okay. So, I can solve these two simultaneous equation, or if you take this, look at the second equation will be x is equal to okay, minus 2y, and then we can substitute this into this. So, you end up with x is equal to 2 and y is equal to minus 1. Okay. So, how do I do it? If there are two independent variables, okay, I differentiate, partial differentiate with respect to x and with respect to y, and then equate it to 0. So, I will get a simultaneous equation for x and y, I solve them, okay. This is where minima happens. Okay, you have to cross check whether it is minima. So, what do? You take the second derivative. So, we have dz by dou z by dou x, we call it, because it is partial. So, again differentiate with respect to x, for example. So, it comes to 4, take dou z by dou y, and you differentiate with respect to y, again it comes to 4. So, both are greater than 0, So like I mentioned in this particular side, so they are greater than 0, so it is a minimum. That is for cross checking actually, okay, it is a minimum. Okay, you can also do the same thing for dou z by dou x dou y. So if you take this equation, okay, what do we get? You are now, instead of differentiating with dou x, differentiate with dou y, so it comes to 2, okay. So again this is greater than 0, so we can say this x is equal to 2, y is equal to minus 1 is the minimum of this particular function, okay. If you draw them graphically, as you can see, the x axis, then this is a independent variable, y axis another independent variable, z is your dependent variable. So it is a parabolic plane, so it goes like this, and you get at x is equal to 2 and y is equal to minus 1, okay, you get the minimum here. So if the functions are very simple, you can do it analytically, okay, like I showed you in the previous case, one variable problem, x is your only independent variable, or in the second problem you have two independent variables x and y, z is your dependent variable, so we can easily do it analytically. But if the function is very complicated with lots of terms, you cannot do that problem analytically. If there are many variables, many independent variables x, y, z, so many, like you in your force field you may have r, you may have theta, you may have phi, so many terms may be there, so many independent variables may be there, so it may be difficult to differentiate and then solve the set of simultaneous equations. So best approach is to do it numerically. That means you get the dou z by dou x numerically, dou z by dou y numerically, and then try to calculate the values where the function will be minimum, okay. So that is how softwares do actually. So that is called the numerical differentiation, they call it numerical differentiation. So we will look at some of these numerical differentiation, numerical integration. You must have studied in your as I said, the first semester or second semester UG engineering courses, or even in 11th and 12th standards, okay. So I am sure you must have studied. Let us not spend much time. Okay, so there are many energy minimization methods. The derivative method, so where you calculate the first derivative or you calculate Hessian. We have the steepest descent method, that means you take the direction in which the slope descends very steep and follow that. So moves are made in the direction parallel to the net force. And then we have conjugate gradient, the gradients in the direction of successive steps are orthogonal, okay. So if you move in one direction, next time you move in the second direction, third time you move in the third direction, like that, you know, each one is orthogonal to another, okay. And then you have the Newton-Raphson, this is again based on some sort of a gradient method, okay. Gradient method is basically derivative based method. You can use Hessian or you can use first derivative and so on. Then second order method, like I said, we have the first and second derivatives are used, then quasi Newton method, built up the inverse Hessian matrix, that is d square f d square f by dx square or dx dy, like that, you know, that is called the Hessian matrix. So different methods are there, some of them are very time consuming because it involves a lot of terms to be calculated, so it requires a lot of computational effort, but then minimization of a function is always a challenge, okay. Minimization of a function is challenge, especially when you have a lot of independent variables, okay. So it is not very straightforward. So a lot of methods are used in the softwares. So if you look at the softwares, even I think if you use Marvin, they also have different methods for energy minimization. I think I did not show it to you, but you can have a look at it, and as you can see there are different methods for energy minimization, okay. How do you know it is enough to stop? Okay, we keep trying to change until we get the minimum values. How do you know when to stop? When there is a very small change in energy, that means I get a confirmation, I have some energy. When I get another confirmation, the change is very small, okay, then I would say let me stop. So, very small means I may give a number like if the difference is 0.01 kilocals per mole, there is no point, you may stop. Or if I am interested in more accurate, I may say 0.001 kilocals per mole. Okay, so depending upon number I feel, I may give. Another approach is small change in the gradient. So, you calculate the gradient, all the gradients, square root, okay, you say there is not much change, very little change in the gradient. Third approach is small change in the root mean square gradient, okay. So, gradient divided by square of n. So, these are the different approaches. One is see the energy change. If the energy change between one conformation and another conformation is very small, then you say enough, we have reached our minimum. Or if you look at the gradient, okay, take the square root, add all the gradient, take the square root, and this value you say you give some number, okay, it is less than 0.01. Or you do the RMS gradient, that means you take the gradient, take the square root of n, and that is called the RMS gradient, and then you say if it is smaller than 0.01, enough is enough, we will stop. Okay, these are the different approaches by which you stop the conformational minimum energy conformation. Okay, so time, steepest descent method generally need at least 500 steps to reach your minimum energy, and it may take 40 seconds of the computation time. Conjugate gradient is much faster, the number of steps required is much less, and it also takes less time. Newton-Raphson method, again it takes less number of steps and less time. So, these are, like I said, numerical methods, okay, you must have studied many of them. So, I will not go too much into that because that is not our focus, but there are many numerical differentiation integration methods which are used by all these molecular modeling software to arrive at the minimum energy conformation. Look at this, let us look at your ethane for example. 2 C's are there, you have hydrogen, 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 hydrogen. So, one hydrogen could be sticking out, one hydrogen could be going back. So, it can take many different conformations, the way you look at, no, suppose you are looking at it like this, okay, you may have the hydrogens, okay, the hydrogens almost exactly overlapping looking. So, that will have a higher energy, okay, almost look at them, when the hydrogens all these are almost overlapping each other. Whereas when the hydrogens are well distributed, not overlapping like this, staggered conformers, these eclipsed conformers, because exactly this hydrogen is looking at this looking at this looking at this, so that we call it eclipsed conformer, you do not see all the 6. Whereas if you have this type of conformation staggered, you can see all of them, energy is low, okay. It can be quite large, 2.9 kilocals to, okay, 2.9 kilocals, which is a big number, or 12 kilojoule per mole, okay, that is a big number, okay. That is why you will always see systems holding on to this type of conformation. Let us look at butane, N-butane, okay. Again as you know, N-butane has 4 carbons, okay, 4, 1, 2, 3, 4. So, we have CH3, CH2, CH2, CH3. So, it takes different conformations, okay, staggered, Gaussian, eclipsed, okay, eclipsed, this is staggered, Gaussian, staggered, Gaussian. You see the CH3s here, okay. This is called a staggered anti, okay, different types of conformation. This is taken from this particular reference, okay. organic chemistry 4th edition. So, each one of them has different energy values, the potential energy, as you can see here. Okay. The energies could be of the order of difference, it could be of the order of 4.5 kilocals per mole, okay, 3.8 kilocals per mole, 19 kilojoule, 16 kilojoule and so on actually. Okay. Okay, so depending upon the conformation they take, you are going to have different energy values and it could be quite high. So, look at this resveratrol. Resveratrol is a natural product, it is a phenolic compound, okay, produced by several plants and they exhibit antibacterial activity. It is found in fruits like skins of grapes, blueberries, raspberries, mulberries. Okay. So, it has got 2 benzene ring and there is a double bond here. Okay. This is a CH 2 benzene rings. Okay. There is a OH here and 2 OH here. So, when it occupies this, the energy is 23 kilocals positive. Look at this, it can go to minus 4.3 kilocals, from 23 to minus 4.3 depending upon how these orientation of these 2 phenyl rings are. Okay, from that energies can change dramatically. Look at this has got a minus 1.3, this has got minus 4.3. Okay, so energies can be dramatically different. Okay, a small change the way these 2 benzene rings orient with respect to these double bonds. Chalcone looks like a resveratrol, but it has got a ketone. Okay, there is an alpha beta double bond here. So, we have again phenyl benzene rings here. So, look at this is 35 kilocals, goes down to 16, it goes down to 12. So, the way they hold themselves here, that makes a lot of difference. Okay. So, depending upon the conformation, small changes in the conformation, you see a lot of difference in these energy values. Okay. Okay, we will continue more on this topic of conformation and minimum energies. Okay. Thank you very much for your time.